Now let's do an example of finding absolute maxima and minima over a closed and bounded region. Let's suppose we wanted to find the absolute maxima and minima of f of xy equals x plus y minus xy over the triangle defined by these 3 points. I've taken the liberty of drawing the triangle for your enjoyment. Oftentimes it's helpful to actually draw the domain so we make sure that, well, all the points that we find are actually in the domain, 1. And 2, it can be helpful for finding the boundary and defining how the function behaves on the boundary. So the first step was to find the interior points, the interior critical points. So let's do that. Recall, to do this, we have to take the gradient. So the gradient of f is equal to 1 minus y, comma, 1 minus x. And this was supposed to be equal to the 0 vector. Well, this is only going to happen if we have the point 1, 1. Now we have to ask the question, is this critical point actually in the interior of our triangle? It turns out 1, 1 is right about there. And so yes, in fact, it is in the interior of our triangle. So that's one of our candidate points to be the absolute maxima or minima. Now, the much harder part of this process is usually the second part, where we have to compute or find critical points on the boundary points. So we want to compute how f acts on these 3 lines. So let's take first the line L1, which I'm going to let y equals 0. So that's this bottom one. So I'm going to define the function g1, which is the restriction of f to this bottom line. So g1 of x is f of x0. Well, this is just x, right? So now, to find the critical points, what we need to do is we need to take the derivative. So g prime, or g1 prime of x, well, this is just 1. So it's never equal to 0. So the only points that we have to check are the 2 endpoints. So this is never equal to 0 for any x. So that gives us our endpoints. And here the endpoints are 0, 0, and 4, 0. So that's line 1 done. Line 2, I'm going to take that to be the vertical line, the x equals 0 line. And here I'm similarly going to define a g2 of y, which is going to be f of 0 y, which is just y. So now we do the same process. g2 prime of y is equal to 1, which is never equal to 0. So again, only the endpoints are possible. So in this case, we still have 0, 0, and also 0, 2. Now we already had 0, 0, so the only additional point we get from this is 0, 2. And finally, the last line is a little bit more complicated. So L3 is this line. Well, the equation for that line is y equals 2 minus 1/2 x. So now my third function, g3 of, how many is t? g3 of t is equal to f of t, comma, 2 minus 1/2 t, which after you do some algebra, you get this to be 1/2 t squared minus 3/2 t plus 2. Okay, so now we've figured out what g3 is. We apply the same procedure. g3 prime of t, this is t minus 3/2. So now we have the point where g prime, or g3 prime of t is equal to 0, or the case where t equals 3/2, or x equals 3/2 in this case. So we have 3/2, comma, whatever this comes out to be, 2 minus 3/4 is 5/4. Something like that. So that should be x equals 3/2, roughly that point. Okay, so now we have 1, 2, 3, 4 points to check, 5 points to check. Let's find the value of f on all of these points. So x, y, again, let's make a chart, f of x, y. So this is 0, 0, 4, 0, 0, 2, what was this one? 3/2 and 5/4, and lastly our 1, 1. Computing these, we have 0, 4, 2, 7, 8, and 1. So now it's pretty clear that this guy is the largest, and this guy is the smallest. So 0, 0 is the absolute minimum. And 4, 0 is the absolute maximum. Now with some creativity, you probably could have figured this out just by looking at the function and the domain, but this is the procedure that will always work.